Welcome to the peaceful space of sleep-friendly science where we float through the cosmic tapestry, exploring the silent, grand expansion that is constantly unfolding all around us. Imagine the space between the stars, not as an empty void, but as a living, breathing fabric. Tonight, we gently unravel the mystery of this cosmic expansion, a quiet, invisible process happening since the dawn of time. We'll softly explore the question, just how fast is space growing around us? Now, settle in, take a deep breath, and let the soft sounds guide you as we begin tonight's journey into the unknown. Section 1, The Silent Departure. Your journey has already begun. It started the moment you decided to rest, to close your eyes and let the world outside soften and fade. Here, in this quiet space, your mind is like the deep, dark sky on a moonless night, vast, open, and ready to be filled with gentle light. Let your awareness drift upward into that imagined sky. Picture it as you have seen it 1,000 times before. A velvet black canvas, punctured by the diamond dust of distant stars. Some are brilliant, sharp, and confident, like lonely diamonds on dark cloth. Others are faint, shy, a mere whisper of light that has traveled for an eternity just to reach you. And there, if you are lucky, you might see the soft, milky brushstroke of our own galaxy, the Milky Way arching overhead like a celestial river. There is a profound stillness in this view, a sense of permanence, of ancient and unchanging peace. For millennia, we looked up at this very same sky and saw a portrait of eternity. The stars were fixed points of reference. The constellations were reliable patterns, a divine clockwork whose hands never moved. The universe, it seemed, was a grand, static cathedral, majestic, silent, and complete. It was always here, and it would always be here exactly as it is. This idea is comforting, isn't it? The thought of something so immense, so powerful, being constant. A reliable anchor in a world of change. It was a belief held not just by poets and philosophers, but by the greatest scientific minds. The universe was a finished masterpiece, hung in the gallery of existence. But light, you see, is more than just something to be seen. It is a messenger. It carries stories. Every single photon that travels from a distant star and ends its long journey in your eye is carrying a secret history. It holds the chemical signature of its parent star, the story of its birth, its life, and its age. And it carries something else, a subtle clue about its motion. A whisper about its journey through the fabric of space. To understand this whisper, let's leave the stars for a moment and think about sound. Imagine you are standing by a quiet road in the countryside. In the distance, you hear the soft hum of an approaching car. As it gets closer, the pitch of the engine seems to rise, becoming higher and more urgent. Neo. Then, just as it passes you, the sound changes dramatically. The pitch drops, becoming lower, deeper as it speeds away. Neo-yom. You've experienced this 1,000 times. It's a simple, intuitive part of our world. The sound waves are being compressed as the car approaches you, making the pitch higher, and they are being stretched out as it moves away, making the pitch lower. Now, let's return to the silent cosmos. Light, just like sound, travels in waves. It doesn't have a pitch, but it does have a color. The spectrum of visible light, from violet and blue to orange and red, is just like a musical scale for light waves. Blue light has shorter, more compressed waves, like a high-pitched sound. Red light has longer, more stretched-out waves, like a low-pitched sound. So, if a star or a galaxy were moving towards us at an incredible speed, the light waves it emits would be squeezed together. Its light would be shifted towards the bluer end of the spectrum. We call this a blue shift. And if that same star or galaxy were moving away from us, the light waves would be stretched, pulled long and thin across the vastness of space. Its light would be shifted towards the red end of the spectrum. A redshift. In the early 20th century, a patient and meticulous astronomer named Vestos Slipher spent long, cold nights at the Lowell Observatory in Arizona doing something no one had ever done with such precision. He wasn't just looking at the stars, he was listening to their light. Using a special instrument called a spectrograph, he could take the light from a distant celestial object and spread it out into its rainbow of constituent colors like a prism. Within this rainbow were dark lines, unique fingerprints that revealed the elements inside the object. Slipher was focused on faint, fuzzy patches of light that were then called spiral nebulae. At the time, no one knew for sure what they were. Were they clouds of gas within our own Milky Way, perhaps new solar systems in the process of being born? Or were they something far, far more distant? Slipher's goal was to measure their motion. He expected to find a random assortment of movements. The universe, in its static grandeur, should be a cosmic dance. Some nebulae should be moving towards us, showing a blue shift. Some should be moving away, showing a red shift. Some should be circling, a gentle, chaotic ballet on a cosmic scale. He began his work, night after patient night, capturing the faint light from these mysterious spirals. He analyzed the first one, the Andromeda Nebula. Its light was blue shifted. It was moving towards us. This made sense. A cosmic neighbor, perhaps, caught in a gravitational waltz with our own Milky Way. So far, so good. But then he measured another, and another, and another. A strange and profound pattern began to emerge, one that was not random at all. Of the dozens of spiral nebulae he painstakingly measured, an overwhelming majority of them were redshifted. Their light was stretched, their song was a lower pitch. They were all moving away from us. And not just moving away, but racing away at incredible speeds, hundreds, even thousands of kilometers per second. Imagine his quiet wonder, alone in the observatory dome in the dead of night. The universe he was observing was not the static, peaceful cosmos everyone believed in. It was as if he had put his ear to the tracks of the universe and, instead of silence, he heard the sound of 1,000 trains all leaving the station at once, all heading away from him. It was a silent, coordinated departure on a scale never before imagined. This was more than just a curious observation. It was a crack in the very foundation of cosmology. Why would everything be moving away from us? Are we at the center of some great cosmic explosion, a place of cosmic repulsion? The idea seemed preposterous, a return to an ancient, self-important view of humanity's place in the cosmos. The stillness of the night sky, the one you imagined just moments ago, was revealed to be a magnificent illusion. It is an illusion born of immense distance and the slow, patient pace of cosmic time. The stars are not fixed. The galaxies are not still. The silence is filled with a hum of departure, a collective redshift that whispers of a universe in motion. Those faint, fuzzy patches of light were not just gas clouds in our backyard. They were sending us a message. A message that the universe itself had a story, a history, and a dynamic nature that was far grander and more mysterious than anyone had ever dreamed. Slipher had detected the first note of a symphony that was playing all around us, but it would take another brilliant mind to arrange those notes into music, to transform the observation of departure into a revolutionary understanding of space itself. The mystery was no longer if the universe was moving, but how. And what were those faint, retreating smudges of light, really? The answer would require a new map, a new yardstick for measuring the heavens, and a journey into distances so vast they challenged the very limits of our imagination. The quiet departure was just the first clue. The grand revelation was yet to come. Section 2. Charting the Cosmic Ocean. The whispers have been heard. The silent departure has been noted. A universe, once thought to be a serene and static painting, is now humming with motion. The vast majority of the faint, swirling nebulae are moving away from us, their light stretched into a mournful, rosy hue. But this knowledge is like hearing a sound in the dark. You know something is there, and you know it's moving, but you don't know how far away it is. You can't see the shape of the room. To understand the true meaning of this cosmic retreat, we needed a map. We needed a new kind of explorer, a cartographer for the cosmos. And so, our journey takes us to the clear, thin air of a mountain in California, to the great Mount Wilson Observatory. Here, under a vast, dark sky, a new instrument had been built, the Hooker telescope, the most powerful in the world. Its giant mirror, 100 inches across, was a colossal eye designed to gather the faintest, most ancient light. It was a portal, a window into the deep, and the man who spent his nights looking through it was Edwin Hubble. Hubble was a different kind of astronomer. He was meticulous, patient, and driven by a grand vision. He was not content to simply catalog what he saw, he wanted to understand its structure, its scale. He was haunted by the same question that troubled Slipher: what were these spiral nebulae? And crucially, how far away were they? Think about the challenge for a moment. Imagine you are in a completely dark room and you see a single, faint point of light. Is it a tiny firefly hovering just inches from your face? Or is it a bonfire on a distant hill miles away? From its brightness alone, you cannot tell. This was Hubble's dilemma. The faintness of a nebula could mean it was small and close, or that it was unimaginably large and mind-bendingly far away. To solve this, he needed a cosmic yardstick. He needed a standard candle. A standard candle is a beautiful idea. It's an object whose true, intrinsic brightness is known. Just like you know the true brightness of a 100-watt light bulb. If you see one far down a long, dark road, you can tell how far away it is just by how dim it appears. The dimmer it looks, the farther away it must be. The question was, did the universe contain such reliable light bulbs? Were there stars that broadcast their true nature across the void? The key had actually been discovered years earlier by a remarkable astronomer named Henrietta Swan Leavitt. While meticulously studying photographic plates, she noticed a peculiar type of star called a Cepheid variable. These stars are not constant. They are alive with a rhythmic pulse. They breathe. Over a period of days or weeks, they swell and brighten, then shrink and dim with a clockwork regularity. And here is the magical discovery she made. Leavitt found a direct, precise relationship between the speed of a Cepheid's pulse and its true, absolute brightness. The faster it pulsed, the dimmer its true nature. The slower its grand, lazy pulse, the more brilliant it truly was. It was as if each star was broadcasting its own wattage. If you could measure the rhythm of its heartbeat, you would know its true power. Henrietta Leavitt had found the standard candle. She had forged the key. It was Hubble who would take that key and unlock the universe. So, Hubble aimed the Great Hooker telescope at the largest and most famous of the spiral nebulae, Andromeda. Night after patient night, he took long exposure photographs, capturing its faint, swirling arms on glass plates. He was hunting for those special breathing stars. It was painstaking work, comparing plates, searching for a single point of light that changed its brightness over time. And then, one night in 1923, he found one. A single, tiny star, a pinprick of light buried in the creamy swirl of the nebula, was pulsing. He carefully measured its rhythm, the time it took to brighten and dim. The pulse was slow. Using Leavitt's law, he knew this meant the star was intrinsically, powerfully brilliant. Yet, in his telescope, it appeared incredibly faint, a mere ghost of its true self. The faintness told him its distance. He performed the calculation, and the number that emerged was stunning. It was a number that broke cosmology. The distance to this single star in Andromeda was nearly 1,000,000 light years. 1,000,000 years for its light to journey to his telescope. Think of what that meant. Our own Milky Way galaxy, which we thought was the entirety of the universe, was perhaps 100,000 light years across. This nebula, this faint smudge in the sky, was nearly 10 times farther away than the edge of our own galaxy. It could only mean one thing. Andromeda was not a cloud of gas inside our cosmic home. It was not a budding solar system. It was an island universe. A galaxy in its own right, just as vast and magnificent as our own Milky Way, populated by hundreds of billions of its own stars, its own planets, its own mysteries. It was a sibling city of light, separated from us by an ocean of darkness so profound it had defied comprehension. In that moment of calculation, the known universe expanded 1,000,000,000-fold. It was one of the most profound and humbling discoveries in human history. We were not the center of everything. Our galaxy was not the sole inhabitant of the cosmos. We were one island in a cosmic archipelago of literally countless others. Every single one of those faint, fuzzy nebulae that Slifer had seen racing away from us was another galaxy, another grand metropolis of stars. This discovery was the birth of modern cosmology. The universe was not a single state, it was an archipelago of nations. Now Hubble had his yardstick. He could turn his telescope to other nebulae, find their Cepheid stars, measure their pulse, and calculate their distance. He became the first true cosmic cartographer, charting the positions of these distant island universes. For the first time, we had a sense of the sheer scale of our reality. A three-dimensional map of the cosmos began to take shape. But this map held an even deeper secret. Hubble now possessed two critical pieces of information for each galaxy. From his own work, he had its distance. And from the pioneering work of Vesto Slifer, he had its speed of recession, its redshift. He had a list. Galaxy A, this far away, moving this fast. Galaxy B, that far away, moving that fast. He began to plot these two sets of numbers against each other on a graph. Distance on one axis, speed on the other. He was looking for a pattern, a connection between these two fundamental properties. Would it be random? Would there be any relationship at all between how far away a galaxy was and how fast it was fleeing? As he placed each galaxy as a point on his chart, a simple, elegant, and earth-shattering pattern began to emerge. The straight line. The data was speaking, revealing a cosmic rule of breathtaking simplicity. The farther away a galaxy was, the faster it was moving away from us. It wasn't a chaotic departure. It was an orderly, stately, and profoundly organized expansion. A galaxy twice as far away as another was receding twice as fast. One 10 times farther away was receding 10 times as fast. The universe wasn't just expanding. It was expanding with a beautiful mathematical grace. The silent departure was not just a movement, it was a symphony, and Hubble had just discovered its melody. Section 3, the expanding symphony. There it is. A simple line on a piece of paper. A collection of points, each one a galaxy, a majestic city of stars, now reduced to a humble dot. But these dots, arranged by the patient hand of Edwin Hubble, are singing. They have formed a chorus, and their song is one of perfect cosmic harmony. The relationship is undeniable, a law written into the very structure of existence. The farther away a galaxy is from you, the faster it is running away. Your first thought, your first human instinct, might be to feel a sense of cosmic importance. If everything is moving away from us, surely we must be the center, the point of origin. It feels like standing at ground zero after a great, silent explosion, watching all the debris fly outwards from where you stand. It's a powerful image, but it's an illusion. It is the last vestige of an old way of thinking, of a universe that revolves around us. The true meaning of Hubble's line is far more profound, more democratic, and more beautiful. To understand it, let us leave the cold vacuum of space for a moment and drift into a warm, fragrant kitchen. Imagine a baker preparing a loaf of raisin bread. The baker kneads the dough, a soft, pliable universe, and then carefully mixes in the raisins. Each raisin is a galaxy. The baker places the loaf in a warm place to rise. Now settle your awareness inside one of those raisins. Let's call it Raisin U. You look around at the other raisins embedded in the dough around you. There's a raisin nearby, just a little way off. There's another one a bit farther away, and a third way over on the other side of the loaf. The baker turns up the heat, and the yeast in the dough begins to work its magic. The dough begins to rise. It expands. From your perspective, inside Raisin U, what do you see? You watch the nearby raisin. As the dough between you and it expands, it begins to move away from you. Not very fast, just a gentle drift. Now look at the second raisin, the one that was already farther away. There is more dough, more expanding space between you and it. So, as the entire loaf swells, that raisin moves away from you faster than the first one. And the third raisin, the one on the far side of the loaf? There is a huge amount of dough between you and it. As all of that dough expands at once, that distant raisin appears to be racing away from you at a tremendous speed. The farther away the raisin, the faster it seems to recede. It is the exact same law that Hubble saw in the sky. Now here's the crucial, wonderful part of this thought. Let's imagine you could instantly transport your awareness to any other raisin in the loaf. The one that was closest to you or the one on the far side. What would you see from there? You would see the exact same thing. From the perspective of any raisin, all the other raisins are moving away and the farther ones are moving away faster. There is no center to the expansion. The center is everywhere and it is nowhere. The expansion is happening in the dough itself, in the very substance of the loaf. No single raisin is special. Every raisin is a valid observer experiencing the same majestic, uniform expansion. Now let us float out of that warm kitchen and back into the cool, silent cosmos. The galaxies are the raisins. And the dough is space itself. This is the paradigm shift that turns cosmology on its head. The galaxies are not flying through space like bits of shrapnel from an explosion. That would imply that space is a pre-existing, empty arena that the galaxies are moving within. The truth is far more strange and elegant. The fabric of space-time itself is what is expanding. The galaxies are, for the most part, just sitting still, carried along for the ride. They are like boats at anchor on a cosmic river, and it is the river itself that is flowing and widening, carrying the boats further and further apart. This is why we see every galaxy moving away from us. It is also why an observer in any of those distant galaxies would look out their own telescopes and see us moving away from them along with every other galaxy in their sky. There is no privileged position. We are all participants in this grand, unfolding cosmic breath. Hubble's discovery gave us more than just a concept. It gave us a number. The steepness of that line on his graph, the precise relationship between distance and speed, is a value known as the Hubble constant. You can think of it as the tempo of the universe. It is the rate of the cosmic expansion, the rhythm of the universal breath. It tells us how much new space is being created every second. The number is usually expressed in a strange-sounding unit, kilometers per second per megaparsec. It sounds complex, but the idea is simple. A megaparsec is just a unit of cosmic distance, a truly immense one, equal to about 3.26 million light-years. So, what the Hubble constant tells us is this: for every 3.26 million light-years you travel out into space, the expansion of the universe carries galaxies away from you that much faster. It's like a cosmic speed limit that is constantly increasing with distance. The space right here, in this room, between you and the wall, is expanding. The space between the Earth and the Moon is expanding. But the amount is so infinitesimally small on these scales that the force of gravity and the forces holding matter together completely overwhelm it. The loaf is rising, but the raisins themselves are not swelling. Gravity holds our galaxy together, it holds our solar system together, and it holds you together. But on the vast, intergalactic scales across millions of light-years where gravity's grip is weak and tenuous, the expansion wins. The cosmic breath is the dominant force. It is a gentle, persistent, and cumulative process. Over these immense distances, the tiny expansion of every bit of space adds up, creating the colossal recession speeds that Slipher and Hubble observed. The universe, then, is not an empty stage. It is an active participant. Space is not a static backdrop, it is a dynamic, growing, stretching medium. The silent, static cathedral of old has been replaced by a living, breathing entity, a symphony whose music is the creation of space itself. This revelation, born from a simple line on a graph, is one of the pillars of modern science. It changed everything. It meant the universe had a history. If everything is expanding now, then in the past, it must have been smaller, denser, and hotter. If you run the movie of the cosmos backwards, all of the galaxies, all of this expanding space, rushes back together towards a single point, a moment of unimaginable density and energy. A beginning. The Big Bang. But that is a story for another time. For now, just rest in this new understanding. Feel the gentle, rhythmic pulse of the cosmos. You are not a spectator watching a distant show. You are inside the symphony. You are part of the rising loaf. The very space around you, the space you are breathing in, is part of this ancient, majestic, and ongoing act of creation. The discovery of the expansion was not an end, but a beginning of a much deeper mystery. What is the space that can stretch? What is this fabric of reality made of? Section 4. The fabric of space-time. The image is a comforting one. A warm, rising loaf of raisin bread. It helps us release the idea of a center, embracing a universe that expands uniformly everywhere at once. The galaxies, our cosmic raisins, are carried along on this swelling tide. But now we must gently press deeper. We must ask a question that takes us from the realm of baking into the very heart of reality. What is the dough? What is this substance we call space, that it can stretch and grow and carry entire galaxies with it? For most of human history, space was simply emptiness. A void. It was the nothing that existed between the somethings. It was the blank canvas, and the stars and planets were the paint. It did not act, it merely contained. It was passive, absolute, and unchanging. But for the uniform expansion to be true, for the very dough of the cosmos to be rising, space must be a thing. It must have properties. It must be an actor in the cosmic drama, not just the stage. To grasp this, we must turn our journey toward the mind of one of humanity's great dreamers, Albert Einstein. He was a man who conducted his most important experiments not in a laboratory with beakers and wires, but inside the quiet cathedral of his own imagination. He looked at the universe and saw not just objects and forces, but relationships, patterns, and a hidden geometry. And in his general theory of relativity, he gave us a new language to describe the cosmos and a new name for the dough, spacetime. It's a beautiful word, spacetime. It tells us that space and time are not separate entities. They are inextricably woven together into a single, four-dimensional fabric. You cannot move through space without also moving through time. You cannot affect one without affecting the other. This fabric is the universe. Let's try to feel this fabric. Imagine, if you will, a vast, flat, infinitely stretching trampoline. It is pulled perfectly taut, a smooth, featureless plane. This is space-time in its simplest form, empty of matter and energy. It is the blank canvas of Newton. Now let's take a heavy bowling ball and place it gently in the center of the trampoline. What happens? The fabric sags. The bowling ball creates a deep, smooth depression, a curve in the surface. It has reshaped the very geometry of the fabric around it. This is what mass does. A star, a planet, a galaxy, even your own body is a mass that creates a dip in the fabric of space-time. The more massive the object, the deeper the curve. Now let's take a small marble and roll it near the bowling ball. What path does it take? It doesn't roll in a straight line anymore. It is caught by the curve, and it begins to circle the central depression, following the contour of the dip. From the marble's perspective, it's just trying to go straight. But the straight line itself is now curved. This is Einstein's vision of gravity. Gravity is not a mysterious, invisible force pulling the marble towards the ball. Gravity is the shape of space-time. The Earth is not being pulled by the sun. The Earth is simply following a straight line through the curved space-time created by the sun's immense mass. It is a cosmic dance, but the choreography is written in the geometry of the universe itself. We live inside a curved reality. Now hold this image of the trampoline with its dips and wells created by the galaxies. We now have a picture for the dough. It is this flexible, geometric fabric. But how does it expand? Let's imbue our trampoline with a magical quality. Imagine that the material of the trampoline itself is alive. It is imbued with an inherent tendency to grow. Slowly, constantly, and uniformly in every direction, the fabric is stretching. The threads are getting longer. What happens to our cosmic objects? The marble, a star, rolling around the bowling ball, its galaxy's center, is hardly affected. Its orbit is small, and the local curve of gravity is overwhelmingly strong. The dip holds it firmly in place. The raisin, as we said, does not expand. But what about another bowling ball, another galaxy, in another depression far across the trampoline? As the fabric between the two of them stretches, the distance between the two depressions grows. They are not rolling away from each other. They are being carried apart by the fundamental expansion of the medium they are resting on. The space between the galaxies is what is growing. This is the very heart of it. This is the mechanism of the expanding symphony. It is a stretching of the fundamental fabric of reality. And this idea solves another beautiful puzzle, the redshift. Remember Vestos Slipher's discovery? The light from distant galaxies is stretched, its wavelength shifted to red. We first thought of it like the sound of a receding car. But now we have a more profound picture. Imagine a single photon of light as a tiny vibration, a ripple sent out across the surface of our stretching trampoline. It is launched from a distant galaxy, a tiny wave traveling through space-time to reach us. While this little ripple is on its long journey, the fabric it is traveling through is itself being stretched. The path of the light wave is elongated. The wave itself, a part of the fabric, is stretched out along with it. So when the light finally arrives at our telescope after millions or billions of years, its waves are longer, more drawn out than when they began their journey. They have been redshifted not because the galaxy is flying away through space, but because space itself has stretched during the light's long voyage. The message has been altered by the journey. The light carries within its very wavelength the history of the cosmic expansion it has traveled through. So now, as you rest here, feel the space in the room. The seeming emptiness around you is not nothingness. It is a substance. It is this pliable, four-dimensional fabric of space-time. It is the medium of existence. It curves and dips around the earth, holding you gently in its gravitational well. It is stitched together with time, carrying you forward moment by moment. And on the grandest of scales, it is imbued with an ancient, ongoing motion of expansion, a quiet, invisible stretching that is carrying distant galaxies farther and farther from our cosmic shore. We have journeyed from a sky of fixed points to a universe of fleeing galaxies, and now to the very nature of the space between them. We have discovered that the stage is not separate from the play. The stage is the play. But this raises a new, profound question. If the universe is expanding today, and it was smaller yesterday, and smaller still the day before that, what happens if we follow this stretching fabric back to its very beginning? Is there a witness to the birth of this expansion? Is there an echo of the first moment, still whispering through the cosmos today? Section 5, The First Light's Whisper. We have journeyed far. From the quiet awe of a starry night to the mind-bending reality of a stretching, living space-time. We have come to understand that the universe is not a static place, but a dynamic, unfolding story. A story of expansion. And like any story, it has a beginning. If the universe is expanding today, if the fabric of space-time is constantly stretching, then in the past it must have been smaller. The cosmic trampoline must have been less stretched. The galaxies, those heavy bowling balls resting on its surface, must have been closer together. Let's run the movie of the cosmos in reverse. Let your mind become a cosmic projector, rewinding the grand film of existence. The galaxies, now rushing away from us, begin to reverse course. They draw closer. The vast, cold emptiness between them shrinks. As they get closer and closer, the universe as a whole becomes more and more dense. The light from a billion stars is concentrated into a smaller and smaller volume. The universe becomes brighter. It becomes hotter. Rewind further. 1 billion years. 5 billion. 10 billion. The galaxies themselves begin to merge, their stars and gas clouds flowing together. The universe is no longer a dark space with points of light. It is a single, glowing fog. The density and temperature climb to unimaginable levels. The very atoms that make up our bodies, the carbon, the oxygen, would be torn apart by the sheer heat and pressure. We rewind past the birth of stars, past the formation of the first atoms, to a time when the entire observable universe was packed into a space smaller than a marble. A searing, opaque, impossibly hot and dense plasma. A cosmic soup of fundamental particles and pure energy. And then we rewind to the very beginning. A moment. A point of infinite density, infinite temperature. A singularity. a beginning of space and time itself. The moment we call the Big Bang. This was the theoretical conclusion of the expanding universe. It was a staggering, almost unbelievable idea. And for many years it was just theta beautiful theory, a mathematical consequence of Hubble's line on a graph. But science requires evidence. It requires a prediction that can be tested. If the story of a hot, dense beginning were true, could there be any leftover evidence? Could there be a fossil, an echo from that first fiery age, still lingering in the universe today? In the 1940s, a few visionary physicists, led by George Gamow, reasoned that there should be. They imagined the very early universe in its first few 100,000 years. It was a truly alien place. A blistering, glowing fog, so hot and dense that light could not travel freely. Photons, the particles of light, were constantly being scattered and absorbed by a sea of charged particles, protons and electrons. The universe was opaque, like being inside the sun. A photon could not travel more than a few inches before crashing into an electron. But the universe was expanding, and as it expanded, it cooled. Like steam thinning out and becoming transparent, the cosmos was on a journey towards clarity. And it was approaching a critical threshold. A magical temperature of about 3,000 degrees Celsius. At this temperature, the universe was cool enough for the frantic electrons to finally be captured by the protons, forming the first stable, neutral hydrogen atoms. It was a moment of profound transformation, a cosmic event called recombination. And in that moment, the universe changed from opaque to transparent. Suddenly, the photons that had been trapped in the cosmic fog were set free. The fog lifted. For the very first time, light could travel unimpeded across the cosmos. This was the first light of the universe. A great flash of brilliance released everywhere at once, in every direction. The universe, in an instant, became see-through. Gamow and his colleagues predicted that this ancient light, this afterglow of creation, should still be detectable today. It should be filling all of space, coming at us from every direction we look. A faint, primordial hum, the oldest sound in the universe. But they reasoned this light would have changed. For the past 13.8 billion years, this first light has been traveling through an expanding universe. And just like the light from a distant galaxy, its waves must have been stretched profoundly. What was once the brilliant, white-hot light of a 3,000-degree fog would have been stretched and stretched, its energy dissipating, its wavelength elongated all the way from visible light, past the red, past the infrared, into the microwave part of the spectrum. The fiery roar of the Big Bang would have cooled to a faint, ghostly whisper, a background radiation with a temperature just a few degrees above absolute zero. It was an astonishing prediction. A testable fingerprint of the Big Bang. But for years, nobody looked. The technology was not quite there, and the idea remained a fringe, albeit beautiful, piece of theoretical physics. Then, in 1965, our story takes us to a laboratory in New Jersey. Two radio astronomers, Arno Penzias and Robert Wilson, were working with a large, horn-shaped radio antenna. It was a sensitive instrument designed to pick up faint radio signals from space. But they had a problem. A persistent, annoying hiss. A background noise that they just couldn't get rid of. It was coming from everywhere. No matter where they pointed their antenna in the sky, the hiss was the same. Day and night, summer and winter. They checked their equipment, rewired their systems. They even famously cleaned out the pigeon droppings from inside the antenna, thinking it might be the source of the interference. But the hiss remained. A uniform, faint, and inescapable whisper from the cosmos itself. They were frustrated. They were astronomers trying to look at specific things, and this cosmic static was getting in the way. Unbeknownst to them, just a few miles away at Princeton University, a team of physicists was busy building their own detector, specifically designed to go hunting for the very microwave background that Gamow had predicted. Eventually, word traveled. The two groups spoke. The moment of realization must have been electric. The frustration of Penzias and Wilson transformed into breathtaking discovery. The annoying hiss that they had tried so hard to eliminate was not noise. It was the signal. It was the oldest story in the universe. It was the echo of the Big Bang. The first light finally reaching us after a journey of 13.8 billion years. It was the whisper of creation cooled by eons of expansion to a faint microwave glow, just as predicted. This discovery, the cosmic microwave background radiation, was a stunning confirmation of the Big Bang theory. It was like finding a fossilized sound wave from the birth of time. When we map this background radiation across the entire sky, we are looking at a photograph of the infant universe. A baby picture of the cosmos when it was just 380,000 years old. It is the earliest possible view we can ever have of our universe, the ultimate wall behind which lies the fiery fog of the beginning. And this picture is almost perfectly uniform. The temperature of this ancient light is the same in every direction to an astonishing degree of precision, about 1 part in 100,000. This uniformity is the ultimate proof of the raisin bread analogy. The early universe was incredibly smooth and evenly distributed. The expansion began everywhere at once in the same way. So, as you rest here, imagine that you can perceive microwaves. The space around you is not dark. It is glowing faintly. It is filled with this ancient, gentle light, a soft, uniform hum that has been traveling since the dawn of time, a constant and gentle reminder that our universe had a beginning. A hot, dense, fiery past. It is the ultimate confirmation that the grand, cosmic expansion is real. But this perfect, ancient light also contains the seeds of a new mystery. If gravity is the force that pulls things together, and the universe began in this hot, dense state, shouldn't the expansion be slowing down? The immense gravity of all that matter and energy, all those galaxies, should be acting like a brake, gently tugging on the fabric of space-time, trying to pull it all back together. For decades, this was the central question of cosmology. Is the universe expanding fast enough to overcome its own gravity and expand forever? Or will gravity eventually win, causing the expansion to slow, stop, and reverse into a big crunch? The universe was locked in a cosmic tug-of-war. Section 6. A cosmic tug-of-war. The universe is filled with a soft, ancient glow, the afterglow of its own creation. This whisper of first light confirms our story. It tells us we came from a place of unimaginable closeness, a hot, dense crucible from which everything we know has expanded. And now a new question settles into the quiet space of your mind, a question of destiny. The universe is engaged in a silent, epic struggle, a cosmic tug-of-war that has been playing out for nearly 14 billion years. On one side of this contest is the past. It is the force of gravity. Imagine gravity not just as a dip in a fabric, but as the universe's memory of that initial closeness. It is the collective pull of every star, every galaxy, every particle yearning to return to that state of unity. Gravity is the great gatherer. It is the sculptor that pulled primordial gas into the first stars, that herded stars into the grand spirals of galaxies, that holds planets in their gentle orbits. It is the force of home, of structure, of pulling things together. In our cosmic tug-of-war, gravity is the anchor, desperately trying to slow the rope, to stop it, and to reel the universe back in. On the other side of the rope is the future. It is the force of expansion. It is the primal momentum inherited from the Big Bang itself. It is the explosive energy of that first moment, still resonating, still pushing outward. It is the desire for distance, for dilution, for a vast and quiet solitude. This expansion is not a force in the traditional sense, but a fundamental property of space-time, a continuous unfolding. It is the very river on which reality flows. So who is winning? For most of the 20th century, this was the single most important question in all of cosmology. The fate of everything depended on the answer. Would the universe expand forever? Or would gravity eventually halt the expansion and pull it all back into a fiery big crunch? A Götterdämmerung on a cosmic scale? To understand the possibilities, let's use a simple earthly image. Imagine you are standing on a planet and you throw a ball straight up into the air. The fate of that ball depends entirely on two things: the strength of the planet's gravity, the cosmic anchor, and the speed at which you threw the ball, the cosmic expansion. First, imagine you throw the ball with a gentle toss. It rises, slows down, hangs for a moment in the air, and then gravity inevitably wins. It falls back to your hand. This was one possible fate for our universe, what cosmologists called a closed universe. If there was enough matter, enough mass, its collective gravity would be strong enough to eventually halt the expansion and reverse it. The galaxies would slow their retreat, stop, and then begin to rush towards each other, culminating in a spectacular and final collapse. Now, imagine you are a giant with immense power. You throw the ball so hard that it achieves escape velocity. It rockets upwards, and although the planet's gravity is still pulling on it, constantly trying to slow it down, it will never be enough. The ball will continue to fly away forever, slowing over an infinite amount of time but never stopping, never returning. This was the second possibility, an open universe. If the initial push of the Big Bang was powerful enough and there wasn't enough matter to rein it in, the universe would expand forever, becoming colder, darker, and emptier as the galaxies receded into an unreachable distance. But there is a third, exquisitely balanced possibility. A destiny that hangs on a knife's edge. Imagine you throw the ball at exactly the escape velocity. Not a fraction more, not a fraction less. It rises, and gravity relentlessly slows it down. It gets slower and slower and slower still. But it never quite stops. It will approach a speed of zero, but only after an infinite amount of time. It is forever poised between escape and return. This was the flat universe or a critical universe. It was the perfect balance point in the cosmic tug-of-war. So, how do we find out which destiny is ours? The answer lay in figuring out the strength of gravity's pull. And that meant weighing the universe. It meant taking a grand cosmic census, trying to figure out just how much stuff, how much matter and energy exists. The tipping point, that perfect balance, was called the critical density. If the universe's actual density was more than the critical density, it was closed and would collapse. If it was less, it was open and would expand forever. If it was exactly equal, it was flat. So, astronomers set to work on this grand, audacious task. They began to count the galaxies in a given volume of space. They estimated the number of stars in each galaxy and the average mass of a star. They measured the vast clouds of gas and dust that drifted between the stars. They added it all up, trying to see if it was enough to tip the scales. And as they did, a strange truth began to emerge. The numbers didn't add up. When they looked at how galaxies were spinning or how they were moving in giant clusters, they saw that the galaxies were behaving as if they were far more massive than they appeared. The stars at the outer edges of a spiral galaxy were orbiting far too fast. By rights, they should have been flung off into the void like children flying off a merry-go-round that's spinning too quickly. The only way they could be held in their orbits was if the galaxy contained a huge amount of extra mass, an extra source of gravity that was completely invisible to our telescopes. This was the first hint of one of the deepest mysteries in all of science, dark matter. It is a substance, a form of matter that does not shine. It does not emit light or absorb it or reflect it. It is a cosmic ghost. We cannot see it. We only know it is there because we can feel its gravitational pull. It is the unseen hand on gravity's side of the rope in our cosmic tug-of-war. This discovery changed the calculation. The universe was far heavier than we thought. Gravity's team was stronger. The possibility of a closed universe, of an eventual big crunch, seemed more plausible. Scientists tried to account for this mysterious dark matter, adding its estimated weight to the cosmic scales. They counted everything they could see and everything they could infer. And after all that work, through the latter half of the 20th century, a consensus began to form. Even with the extra weight of the mysterious dark matter, the total density of the universe still seemed to be less than the critical density. It was close, but it seemed that gravity was destined to lose the fight. The initial momentum of the expansion was just too great. The predicted fate of our universe was a majestic, if lonely one. It would be an open universe, expanding forever. The tug-of-war was still happening, gravity was still pulling, so the expansion should be gradually, almost imperceptibly, slowing down. But it would never stop. It would be like that ball thrown faster than escape velocity, forever coasting into the infinite darkness, its initial burst of speed slowly fading but never failing. This was the picture as the 20th century drew to a close. A universe born in fire now expanding into an eternal, cooling night. The great question seemed to be settled. The battle was long and slow, but the outcome was known. But the universe, it turns out, is full of surprises. Science is a journey of peeling back layers, and beneath this seemingly settled picture, a new, far more shocking reality was waiting to be discovered. The next chapter in our story would not come from weighing the universe, but from once again trying to measure its history, to look back in time and see if the expansion was, in fact, slowing down as everyone expected. The universe had not yet revealed its greatest secret. Section 7. The Unexpected Acceleration. And so, a picture of our universe settles into place, like dust settling in a quiet room. It is a grand and lonely destiny. A universe born in a flash of brilliant energy, now coasting outwards, its initial momentum carrying it into an eternal, ever-expanding future. The great cosmic tug-of-war continues, but gravity, the force of togetherness, is gently losing. The expansion, we believe, is slowing down, but not enough to ever stop. This was the story we told ourselves. It was a reasonable story, an elegant story, a story that made sense. And it was a story that astronomers, being good scientists, set out to prove. The new quest was not just to know the universe's fate, but to witness it, to measure the rate of this cosmic deceleration. To do this, they needed to look deeper into the past than ever before. The faint pulses of Cepheid variable stars, the cosmic yardsticks that Hubble used, were not bright enough. They faded into the noise over these immense distances. To chart the history of the universe billions of years into the past, astronomers needed a new kind of standard candle. They needed something not just bright, but spectacularly, blindingly brilliant. They needed a cosmic lighthouse. And the universe, in its grace, provides one. It comes from a dramatic and violent story of two stars. Imagine a binary star system, two stars orbiting each other in a celestial waltz. One of these stars is a white dwarf, the tiny, dense, dead core of a star that has used up its fuel. It is a cosmic ember, a ghost of a once mighty sun. Its companion is a larger, living star, still full of life and energy. The white dwarf is small, but its gravity is immense. It begins to pull material from its larger companion, siphoning off its outer layers of gas like a silent, cosmic vampire. For thousands of years, the white dwarf feeds, pulling a steady stream of matter onto its surface. It grows heavier, denser, more and more compressed. It is a ticking time bomb, approaching a very specific critical massa precise limit known as the Chandrasekhar limit. And when it reaches that limit, something spectacular happens. The pressure at its core becomes so immense that it reignites in a single, final thermonuclear detonation. The star explodes. It becomes a Type Ia supernova. For a few brilliant weeks, the single exploding star can outshine its entire host galaxy of 100 billion stars. It is a flash of perfectly calibrated brilliance. And here is the magical part, because they all explode at precisely the same mass, they all reach almost exactly the same peak brightness. They are the ultimate standard candles. If you see one of these cosmic lighthouses in a distant galaxy, you can measure how faint it appears and know, with incredible precision, how far away it is, and therefore, how long its light has been traveling to reach you. In the late 1990s, two competing teams of astronomers embarked on a grand project. They began to hunt for these distant explosions. Using the world's most powerful telescopes, they would stare at patches of the deep sky, returning night after night, comparing images, looking for a new point of light that wasn't there before. When they found one, they would measure two things: its redshift, which told them how fast its host galaxy was receding from us, and its faintness, which told them its distance and how far back in time they were looking. Their goal was to measure the slowing of the expansion. The logic was simple and clear. If they looked at a very distant supernova, one that exploded, say, 7 billion years ago, they would be looking at a younger universe. A universe where the expansion was faster, before gravity had as much time to slow it down. Therefore, these distant supernovae should appear brighter than you would expect in a universe expanding at a constant rate. They are, in effect, closer to us than they should be, because the expansion between them and us has been slowing down over all those billions of years. The teams began to gather their data, point by precious point. Each supernova was a postcard from the distant past. They plotted them on their charts just as Hubble had done decades before. Distance versus speed. But this time they were looking for a subtle deviation, a slight curve in the line that would reveal the gentle braking action of gravity. And then they saw it. A result so strange, so profound, so utterly contrary to all expectations that at first they thought it had to be a mistake, a flaw in the data, an error in the telescopes, a miscalculation. The distant supernovae were not brighter than expected. They were fainter, consistently, undeniably fainter. Let this profound shift settle in your mind. Fainter means farther away. These ancient lighthouses, these postcards from a younger universe, were significantly farther away from us than any existing model of the universe could explain. How could this be? How could they be farther away? There is only one way. In the billions of years since that starlight began its journey to us, the space between that supernova and our own galaxy has stretched more than we thought. The expansion of the universe has not been slowing down. It has been speeding up. You can almost feel the collective intake of breath in the world of astronomy. The intellectual vertigo. It was as if you threw a ball into the air and instead of slowing down and falling back, it suddenly ignited its own rocket engine and shot upwards faster and faster into the sky. It was impossible. It defied everything they thought they knew. The cosmic tug-of-war was not what we thought. Gravity was not just losing the fight. Something else, some mysterious, invisible, and powerful force had joined the other side. It was a ghost in the cosmos, a phantom hand that was not just helping the expansion, but was actively pushing on the fabric of space-time, forcing it to accelerate. The universe was not coasting to its future. It was a runaway train gathering speed. The discovery was checked, rechecked, and confirmed by the competing team. It was real. The universe is accelerating. This was and is one of the most revolutionary discoveries in the history of science. It earned its discoverers the Nobel Prize, and it plunged physics into a state of profound mystery. What is this force? What is this energy that seems to arise from the vacuum of space itself, pushing the universe apart? Physicists dusted off an old idea that Einstein himself had once proposed and then called his biggest blunder a cosmological constant, a kind of innate, anti-gravitational energy built into the fabric of space. They gave this mysterious entity a new name, a name that perfectly captures our lack of understanding: dark energy. It is dark because we cannot see it or detect it directly. It is energy because it is having a powerful physical effect on the cosmos. And it is, by far, the dominant player in our universe. When we add up the cosmic budget now, the ordinary matter that makes up you and me and all the stars and galaxies is a mere 5%. The invisible dark matter, the ghost that holds galaxies together, makes up about 25%. And the rest, a staggering 70% of the entire energy budget of the universe, is this mysterious anti-gravitational dark energy. We live in a universe whose composition is dominated by two things we cannot see and do not understand. The discovery of the accelerating expansion was not an answer, but the beginning of a question so deep it shakes the foundations of our reality. What is this ghost in the cosmos? Section 8. The Ghost in the Cosmos. Let the quiet settle around that astonishing thought. The universe is not just expanding. It is accelerating. A discovery that has, in a single stroke, rendered our cosmic map incomplete. We are like ancient mariners who have charted every coastline, every island, every current they know, only to realize that the ocean itself has a will of its own. a deep and powerful tide that is now carrying them, and everything else, towards an unknown horizon at an ever-increasing speed. We have given this force a name that hums with poetry and humility, dark energy. Let's stay with that name for a moment. Feel its weight. It is dark not because it is sinister or evil, but because it is hidden from our sight. It lies beyond the reach of our most powerful telescopes, a ghost that leaves no footprints, casts no shadow. And it is energy because, despite its invisibility, its effects are the most profound in the cosmos. It is the invisible hand that is pushing the universe apart. Before we try to understand what this ghost is, let's be clear on what it is not. It is not dark matter. Dark matter, that other great mystery, is a completely different kind of ghost. Dark matter is gravitational. It clumps together. It is the invisible scaffolding upon which galaxies are built, the unseen mass that holds them together. Think of it as the anchor on gravity's side of the tug-of-war, hidden but heavy. Dark energy is the opposite. It is anti-gravitational. It does not clump. It is smooth, ethereal, and perfectly distributed throughout all of space. It is a phantom pressure pushing outward everywhere at once. It is the wind in the universe's sails. So what could it be? What is the source of this gentle, persistent, cosmic push? The most prominent idea, the one that is both beautifully simple and deeply strange, is that dark energy is the energy of the void itself. It is the cost of having space. Imagine, for a moment, the concept of true, absolute nothingness. An empty box with not a single atom or particle inside. For centuries, we thought of this as empty, a placid, inert, zero-energy state. But one of the most profound discoveries of modern physics is that the vacuum is not empty at all. On the very smallest quantum level, the void is a chaotic, shimmering, effervescent place. It is a quantum foam, where tiny pairs of particles and antiparticles are constantly bubbling into existence from nothing, surviving for a fleeting instant, and then annihilating each other back into nothingness. It is a sea of potential, the silence between the notes of a song, which is itself part of the music, the space around a sculpture, which is part of the art. This constant, simmering activity, this fizzing of virtual particles, imbues the vacuum of space with a baseline energy, an intrinsic energy of existence. This is called vacuum energy. And this energy, according to Einstein's equations, would have a remarkable property. It would behave like an anti-gravity. It would exert a negative pressure. It doesn't pull, it pushes. It is a fundamental tension woven into the fabric of reality itself, causing it to want to expand. If this is true, then dark energy has been here all along. It has been a silent partner in the cosmic drama since the very first moment. So why did we only just notice it? Why did the universe wait for billions of years before it started to accelerate? Let us return to our rising loaf of raisin bread. The raisins are matter and dark matter. The dough is space. The initial push of the Big Bang is like the strong initial action of the yeast, making the dough rise quickly. The gravity of all the raisins, their collective weight, is trying to make the dough collapse back on itself. Now, let's add dark energy to our recipe. Imagine that the dough itself, the very substance of space, has an innate, magical property. It wants to expand. It has a constant, gentle, outward pressure. In the early universe, the loaf was small. The raisins were packed tightly together. The force of their gravity was immense, the dominant power in the loaf. The dough's own desire to expand was still there, but it was trivial in comparison. Gravity was the undisputed king, slowing the expansion down. But as the universe expanded, something crucial happened. The raisins, the matter and dark matter, got farther apart. They were spread more thinly throughout the growing loaf. The gravitational pull between them weakened, just as the pull of a magnet weakens with distance. Gravity's power began to fade. But the dark energy, the magical property of the dough itself, behaved differently. The energy in any given cubic inch of dough remained constant. It did not dilute. It is an intrinsic property of space. So, as the universe grew larger, the total amount of this repulsive energy grew with it. A bigger loaf meant more expanding dough and thus a greater total outward push. The quiet partner was growing in influence. For billions of years, gravity was winning the tug of war, but its grip was slipping. The outward push of dark energy was growing stronger and stronger. And then, about 5 to 6 billion years ago, a cosmic tipping point was reached. The ever-growing, repulsive force of dark energy finally became more powerful than the ever-weakening pull of gravity. The cosmic tug-of-war was over. The ghost had won. From that moment on, the expansion of the universe was no longer slowing down. It began to accelerate and has been doing so ever since, pushed along by the relentless, invisible energy of space itself. Rest with the profound implications of this. The empty space in the room around you is not empty. It is the source of 70% of the energy in the universe. The nothing is more powerful than all the somethings combined. The space between the stars is not a passive void, but an active, energetic medium that is driving the ultimate fate of the cosmos. We are living in a remarkable cosmic era. We exist in that brief, wonderful window after the universe became transparent, but before it has expanded so much that all other galaxies are pushed beyond our horizon, their light unable to ever reach us. We are, perhaps, the only generation of beings who will ever be able to piece together this full story, to see both the echo of the beginning and the evidence of the accelerating future. This idea of vacuum energy is the leading contender for dark energy, but it comes with its own deep, deep problem, a chasm in our understanding. When our best theories of physics try to calculate how much of this vacuum energy there should be, they come up with a number that is staggeringly, comically wrong. It is 120 orders of magnitude, that is a 1 followed by 120 zeros larger than the amount we actually observe. This has been called the worst theoretical prediction in the history of physics. It is a crack in our most fundamental understanding of the world. It tells us that we are missing something profound. And so the ghost remains a ghost. Is it the energy of the vacuum? Or is it something else entirely? A new, undiscovered field or force? Or perhaps, most radically, is our understanding of gravity itself, the great theory of Einstein, incomplete on the most cosmic of scales? The mystery of dark energy is the frontier of modern cosmology. It is a signpost pointing toward a new, deeper physics that we have not yet imagined. It is a whispered invitation to a new level of understanding, one that awaits a future dreamer, perhaps another Einstein, to unravel. Section 9. A crack in the cosmic code. We find ourselves in a universe far stranger than we had ever imagined. A cosmos composed mostly of ghosts, dark matter, and dark energy, and driven by a force we cannot explain, causing space itself to accelerate its own expansion. We have a story, a beautiful model of cosmology that explains so much, from the first whisper of light to the flight of the farthest galaxies. This model, our best understanding of the universe, feels solid. It is built on decades of painstaking observation and brilliant theory. And yet, science is a restless endeavor. It is never content with the current story. It is always testing the foundations, pushing on the walls of our knowledge, looking for the slightest crack. Because a crack is not a sign of failure. It is an opening. It is a hint that there is a deeper, more magnificent room waiting to be discovered. And right now, at the very heart of our understanding of the expanding universe, a crack has appeared. It is a quiet, persistent, and deeply troubling disagreement. A puzzle known as the Hubble tension. The tension is about a single number, but it is one of the most important numbers in all of cosmology, the Hubble constant. Remember this? It is the tempo of the universe, the rate at which space is expanding today. It is the number that Edwin Hubble first estimated with his line on a graph. For decades, astronomers have been on a quest to measure this number with ever greater precision. And now they have become too good at their jobs. They have two different, highly precise methods for measuring the expansion rate of the universe. And they don't agree. Let's explore these two paths to understanding our universe's tempo. The first path is the path of the early universe. It begins with that beautiful ancient light we discover the cosmic microwave background. This is our baby picture of the cosmos, a snapshot of the universe at just 380,000 years old. This is not just a uniform glow, it contains incredibly tiny, subtle variations in temperature. These faint ripples are the seeds of all future structure. They are the slight density differences in the primordial soup that would, over billions of years, grow under the influence of gravity to become the galaxies and clusters of galaxies we see today. Our standard model of cosmology is a powerful recipe book. It tells us exactly how these tiny ripples should evolve over 13.8 billion years. It is a story that includes normal matter, dark matter, and the accelerating push of dark energy. By feeding the precise details of that baby picture, the size and distribution of those ancient ripples into this model, we can run the movie of the universe forward. We can predict what the universe should look like today. And part of that prediction is a very precise value for the Hubble constant. It is a calculation of what the expansion rate must be now, given where it started and the ingredients we know are in the cosmic recipe. Think of this as looking at a newborn child, and with a perfect knowledge of genetics and nutrition, predicting exactly how fast they should be growing as a teenager. This method, based on the pristine physics of the early universe as measured by the Planck satellite, gives us a number. Let's say, for simplicity, it's about 67 kilometers per second per megaparsec. A firm, confident prediction based on our deepest understanding of cosmic history. Now, we turn to the second path, the path of the late universe. This is the direct approach, the spiritual descendant of Edwin Hubble himself. It involves measuring the distances and speeds of things in the universe around us today. It doesn't rely on a model of the past, it just observes what is happening right now. This is the path of the cosmic lighthouses, the Cepheid variable stars, and the Type I supernovae. Astronomers have spent years refining this method, creating what they call a cosmic distance ladder. They start by measuring the distances to nearby Cepheid stars with incredible precision. Then they use those stars to calibrate the distances to farther galaxies where they can also see Type I supernovae. Then they use those calibrated supernovae, those perfect standard candles, to measure the distances to even more remote galaxies, billions of light years away. It's a meticulous, step-by-step process of building a ruler to measure the modern universe. By comparing the distances they measure with the redshifts of those galaxies, they can calculate the Hubble constant directly. They are simply measuring the line on the graph, just as Hubble did, but with astonishing 21st century precision. This is like measuring the teenager's growth rate directly with a measuring tape and a stopwatch without any assumptions about their past. And this method gives us a different number. It gives a value of around 73 kilometers per second per megaparsec. Let that sink in. 67. 73. They sound close. But in the world of precision cosmology, with the error bars on these measurements shrinking every year, this is not a small discrepancy. It is a gaping chasm. The two best methods we have for measuring the most fundamental parameter of our universe give us two different answers. And the more precise the measurements get, the worse the disagreement becomes. The crack is widening. This is the Hubble tension. It is a profound, fascinating, and thrilling puzzle. It means one of three things must be true. Possibility 1. Someone is wrong. There is a subtle, hidden error in one of the measurements. Perhaps the astronomers measuring the supernovae have a flaw in their cosmic distance ladder. Perhaps the astronomers measuring the early universe have misunderstood some detail about the ancient plasma. This is the most conservative possibility, and scientists on both sides are tearing their own experiments apart, looking for any conceivable mistake. But so far, the measurements have held firm. Possibility 2. Our model is wrong. Our cosmic recipe book, the standard model of cosmology that we use to connect the early universe to the late universe, is missing an ingredient. Maybe there was a new type of particle or energy present in the early universe that we don't know about, something that changed the expansion rate in a subtle way. Something like an early dark energy that gave the universe an extra push for a while before fading away. This would mean our prediction, our calculation of 67, is based on an incomplete story. Possibility 3, our understanding is really wrong. This is the most radical and, for many, the most exciting possibility. It could be that both measurements are correct, and our model is correct, but something more fundamental is at play. Perhaps the laws of physics themselves are not as constant as we assume. Maybe our understanding of gravity, or the nature of dark energy, needs a complete overhaul. The tension could be a sign that we are on the precipice of a revolution in physics, much like the one Einstein sparked a century ago. We are standing at a crossroads. We have a story of the universe that is majestic and powerful, yet it is showing a strain. The beautiful, smooth narrative we have woven from the Big Bang to the present day has a persistent, nagging contradiction at its heart. And this is the beauty of science. It is not about having all the answers. It is about the thrill of the question. It is about the humility of finding a crack in your most cherished theories and having the courage to peer inside. The Hubble tension is not a failure. It is an invitation. An invitation to be curious, to be imaginative, and to continue our journey of discovery, knowing that the universe is, and perhaps always will be, more clever and more mysterious than we can possibly imagine. Section 10, Lonely Islands of the Future. Our journey is nearing its gentle end. We have traveled from the comforting stillness of our own night sky to the edge of understanding itself. We are left here, in this quiet, contemplative space, with a profound and beautiful tension, a crack in our cosmic code. The universe, it seems, does not give up its secrets easily. It asks of us not certainty, but a continued sense of wonder. And so we hold these two truths in our minds, like two hands holding starlight. The story of our past, written in the ancient glow of the beginning, and the story of our present, measured in the flight of modern galaxies. They tell a slightly different tale, and in that difference, a new journey of discovery awaits. But while the precise tempo of the cosmos remains a gentle puzzle, the song itself is clear. The great discovery of our age holds true. The universe is accelerating. The ghost in the cosmos, the dark energy woven into the fabric of space, is winning the long tug-of-war. Its quiet, persistent push is the dominant force shaping our ultimate destiny. And so, for our final exploration tonight, let us drift forward. Let us follow the current of this accelerating river, not just for a billion years, but into the deep, deep future to see the universe that is being born from this expansion. Imagine you are standing on a ship sailing away from a vast coastline dotted with innumerable lighthouse beacons. At first, the lights are clear. But your ship is not just sailing, it is accelerating. As you pick up speed, a strange thing begins to happen. The most distant lighthouses, the ones at the very edge of the horizon, seem to freeze. Their light struggles to keep up with your increasing speed. Eventually, you are moving away from them so fast that their light can no longer reach you at all. They wink out one by one, vanishing from your reality. They are still there, shining, but they have crossed a horizon, an edge from which no message can ever return to you. This is the future of our cosmos. As the expansion of space accelerates, it creates a cosmic event horizon. This is not a physical wall, but a point of no return. Galaxies are not just receding from us. They are being pulled away by the stretching of spacetime itself. There will come a time for each distant galaxy when the space between us and it is expanding faster than the speed of light. It is a strange thought, but it does not violate relativity. Nothing is moving through space faster than light. It is space itself that is doing the carrying. And when a galaxy crosses that horizon, it is lost to us forever. The light it emits from that moment on will never reach the Milky Way. We will see the light it sent before it crossed, stretched into an infinitely long, faint, red wave, until the last photon reaches us and it fades to absolute black. It has effectively vanished from our observable universe. Let us drift forward in time. 100 billion years from now. The night sky has changed. It is darker. The rich tapestry of distant galaxies that we see today, the faint smudges of light that inspired Hubble are gone. The accelerating expansion has pushed them all beyond our cosmic horizon. The sky, to a future observer, would be mostly empty. The story of an expanding universe would be almost impossible to read. The evidence would have been erased. But the story is not entirely over. While the grand universal ocean empties, a local drama is unfolding. The force of gravity, while defeated on the cosmic scale, is still the master of its own small domain. Our own Milky Way galaxy is part of a small cluster of galaxies, a little gravitationally bound neighborhood called the local group. Our largest neighbor, the Great Andromeda Galaxy, is one of the few that shows a blue shift. It is not receding. It is on a collision course with us. In about 4.5 billion years, our two majestic spiral galaxies will begin a slow, magnificent dance of merger. Stars will not collide. The distances between them are too vast, but their grand structures will pass through each other, pulling and twisting in a gravitational embrace that will last for hundreds of millions of years. Eventually, they will settle, merging into one single, gigantic elliptical galaxia, new entity sometimes affectionately called Milkomeda. The other smaller galaxies of our local group will one day join it, like rivers flowing into a great sea. Now, let's drift even further into the future. 1 trillion years. Imagine an astronomer, a being of unimaginable patience, living in this great, calm island of Milkomeda. They build their telescope and they look out at the sky. What do they see? They see the trillion stars of their own home galaxy, a vast and beautiful city of light. But beyond it there is nothing. Only an endless, perfect, featureless black. The cosmic background radiation itself will have been stretched to a wavelength longer than the observable universe, rendering it undetectable. All evidence of the Big Bang, all evidence of other galaxies, all evidence of the grand expansion will be gone. These future beings would be forgiven for believing, as our own ancestors did, that their galaxy was the entire universe. A single, static, lonely island of light in an infinite, eternal void. The universe will have given itself a form of cosmic amnesia. It will have hidden its own origin story. And here we find the most profound piece. This future, this lonely fate, is so far away as to be a dream. It is a cosmic poem, not a personal destiny. The story of this ultimate emptiness is not a cause for fear, but a reason for a deep and present gratitude. It tells us that we are alive in a golden age. We are the privileged ones. We live in that perfect, fleeting window of cosmic history where the sky is still full of clues, where we can look back and see the dawn of time and look forward and glimpse the shape of eternity. Our journey tonight, from the first curious glance at a starry sky to the mind-bending reality of an accelerating void, mirrors our own journey into sleep. We begin with the familiar world and slowly we let it expand away from us. The concerns of the day, the thoughts, the plans, let them recede. Let them be carried away on the gentle, expanding current of your breath until they are beyond the horizon of your awareness, leaving only a quiet, peaceful, and dark space. You are your own island universe, full of dreams and light. And for tonight, that is the only universe that matters. Our journey through the expanding cosmos has come to a close. We have floated on the river of space-time, listened to the first whispers of light, and stood in awe before the profound mysteries of a universe that is not just growing, but accelerating into an unknown future. It is a story of immense scale and breathtaking beauty, a reminder that we are part of something ancient, vast, and still unfolding. Now it is time to let these cosmic thoughts dissolve like sugar in warm water, leaving only a feeling of peace and wonder. Let the grandeur of the universe become a gentle lullaby, a quiet reassurance that even in the vast darkness, there is a beautiful and elegant order. You are a part of that order. You are stardust contemplating the stars. Let go of the journey now. Let your awareness rest. There is nothing left to do but to drift into the quiet, personal cosmos of your own deep and restorative sleep. Rest well. Sleep deeply. And may your dreams be as peaceful as a silent, starry night.